Hello everybody, today we'll talk about sonic Doppler effect. So the Doppler effect or Doppler shift is the apparent change in frequency of sound when there's relative motion between the source of sound and an observer. Austrian physicist Christian Doppler described this phenomenon in 1842. The perceived frequency due to Doppler effect can be greater, less, or stay the same based on several conditions, and it's applicable to both sound waves and light waves, but we're going to restrict ourselves to sound waves. In particular, we're going to talk about the Doppler effect that occurs when the object itself is traveling at the speed of sound. If you want to check about the general Doppler effect, check the link in the description below. So the speed of sound is the distance traveled per unit time by a sound wave as it propagates through a medium. For example, the speed of sound in air is approximately 343 meter per second at temperature of 20 degrees C. And the speed of sound changes, as the medium changes or different conditions changes. You can check a detailed video about speed of sound in the link in the description. So in order to travel faster than the speed of sound or even travel at the speed of sound, you need to break the sonic barrier. So in order to break the barrier, one has to travel faster than sound can travel, and this is most important in the medium of interest. Now, if you're talking about medium as air, you need to travel faster than that sound can travel in air. So for example, an airplane that can travel faster than 343 meter per second in air breaks the sonic barrier. Again, temperature is also important because speed of sound changes with temperature. An airplane traveling exactly the speed of sound is said to travel at Mach 1. This is the equation for the Doppler effect. So F is the apparent frequency or the perceived frequency, F0 is the original frequency, C is the velocity of sound in air, V0 is the velocity of observer, and Vs is the velocity of source. Now we will solve several different cases with the help of that equation. So this is the first setup. So an observer as a human is standing stationary and on the ground, and there is an airplane which is coming from point A and going towards point B. So we'll analyze here what's going on. But here's the case. The airplane is moving exactly the speed of sound, so it's moving at Mach 1, and the medium of interest is air. So the first case is the source, which is the airplane moving at the speed of sound, is moving toward a stationary observer. So this velocity of source is the velocity of sound, and the velocity of observer is 0 because it's just a human standing on the road. So if we put in those values, we get F equals infinity because the equation becomes C over C minus C, and we know anything over 0 is infinity or not defined. So what does this mean? Well, it means that the apparent frequency does not exist, but we need to know a deeper meaning. What does it mean physically? I mean, we know that the value is infinity, but what it means physically. So frequency we know is inverse of time. So if frequency is infinity, meaning it's extremely large, so time is 0. It means that there is no sound waves to hear because the plane itself is a source of sound. You can think of it like this. The plane is traveling with the sound. So when the plane does reach the observer initially, he's not going to hear any sound because, the sound waves are also coming with the plane. The observer will be able to see the plane but will not hear anything. But the observer will hear the sound when the plane passes him because, when the plane passes, the sound waves are also passing by. So that's the meaning of infinity frequency. So the next case is the continuation where the plane is moving away from the observer at the speed of sound. So the velocities are still the same. You plug in the apparent frequency is half of the original frequency. So the next setup is a different. So now the observer is moving, whereas the source is stationary, and the source can be considered as an industry emitting sound waves, whereas the observer, on a plane is moving at the speed of sound. He's approaching the source and will be receding away from the source. So let's see what happens here. So this is case 3. The observer on a plane is moving toward a stationary source. So the source is stationary, which means its velocity is 0, whereas the observer is moving at the speed of sound, so its velocity is c. So if you plug all those values in the equation, you get the apparent frequency is twice the original frequency. So the observer is going to hear twice of what the actual frequency is. The next case is observers moving away from the stationary source. This is just a continuation. So again, the source velocity is 0, whereas the observer's velocity is the speed of sound. You plug those equations, we see that the frequency is 0. So again, what does this mean physically? So F is 0, it means that 1 over F should be very large or infinity. So in this case, time is infinity. So sound waves are generated by the source continuously, but the observer, you need to understand that he's actually traveling at the speed of sound. So which means sound waves have to travel then faster so as to reach the observer, so as to catch up with the observer. But they are not fast enough because both are traveling at the speed of sound. So sound waves cannot catch up with the observer who himself is traveling at the speed of sound. So that's why the observer will never be able to hear the sound, but he'll be able to see the source though. The next setup involves both source and observer in motion. So the source is still the plane moving at the speed of sound, whereas the observer is a human, but actually he's running toward the plane. So we'll analyze what's going to happen when the source is approaching the observer and receding away from the observer while the observer is running. And the medium of interest is air, so in this case, they both are moving, so the speed of the source is the velocity of sound, whereas the speed of the observer is not zero, but it's whatever is the speed at which he is running. So we plug the equations. We see that v0 is very small relative to the speed of sound, so it doesn't make any difference. The case is same as the previous case that we have already seen, where f is infinity. So it stays the same. And the next case is when the source is moving away from the observer, but the observer is also running in the opposite direction. Again, the velocities are same. The observer is a non-zero velocity. You plug all the values in, we still see that, since v0 is very small compared to the speed of sound, the answer is still the same. It's going to be almost equal to half of the original frequency. The apparent perceived frequency would be half of the original frequency. So the next setup is a little different. So here we have a source and observer, but in this case, both are moving at the speed of sound and both are moving toward each other. So let's see what happens. So we know both are moving at the speed of sound, so their both velocities are the speed of sound itself. And you plug all those values in, we get f is infinity. And the next case is both are moving away from each other, so they cross each other and they're continuing to move in opposite directions at the speed of sound. Again, the apparent frequency does not exist because they both are moving at the speed of sound. So in order to even hear sound, one has to travel slower than the speed of sound, or sound waves have to travel faster. So that's not happening here, so they don't register any sound waves. The next case is also another case where the source is chasing the observer. So instead of moving in opposite directions, they both are traveling one behind the other, but they are both traveling at the speed of sound. Again, the apparent frequency does not exist in this case. So here's a sound effect or sound of a military jet pass by, which is traveling at the speed of sound. I hope you heard the sonic boom. So to conclude, the Doppler effect or Doppler shift is the apparent change in frequency of sound when there is relative motion between the source of sound and the observer. The apparent frequency is different. It can be greater, lesser, do not exist based on different conditions. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.